In the last session, we focused on the analysis for a TMO in the dielectric slab waveguide. And the calculation appears a little bit complicated. I try to help you to get more familiar with by introducing a TMO in this dielectric slab waveguide. So just try to repeat the analysis a little bit so that you can be more familiar with the process to analyze those modes in a dielectric waveguide. So now we have a T wave inside this waveguide, and the configuration remains the same. We have a dielectric region between y equal to plus or minus d/2, and outside this dielectric region is just vacuum. Previously in section 1, in the first session, we set some arbitrary refracting index here to increase the one freedom to adjust the mode inside. But for this case, we just set this refracting index in the colliding region to be vacuum, to be equal to 1. So we write down the field expression for the T wave, where you have the Z component of the magnetic field inside this waveguide, but we don't have any variation along X direction. And this wave propagates along the Z direction. Therefore, you have a propagation constant gamma equal to J beta. Now, let's put this expression into Helmholtz equation. And then you write down this expression as a function of the Z component of the magnetic field. Again, the eigenvalue will satisfy this dispersion relationship, H squared equal to gamma squared plus the K squared, but the gamma now is equal to J beta. So inside the dielectric region, you have a general solution that could be sine or cosine. And for this sine solution, we call it RT mode. And for this cosine solution, we call it even T mode. For example, if I have this even T mode with a cosine solution, then the Z component of the magnetic field is going to have such a field pattern which is symmetric about this Z axis. On the other hand, if you have a sine-like solution for the magnetic field, then the field pattern is going to be asymmetric for this Z component magnetic field. And in this region, you have a standing wave bouncing in the vertical direction. So you have a Ky in this expression equal to H. And gamma again has a propagation constant of beta. So you put this into this expression to have the first dispersion relationship. And outside the waveguide region is vacuum. So the field outside this region for guided mode is going to be an evanescent wave. So again, you have this exponential decay field expression outside this dielectric region. And the dispersion relationship now is given by this. You have an attenuation constant along y direction, so H is chosen to be J alpha, and gamma again is equal to J beta, because even though it's an evanescent wave, it still propagates along the Z direction. So you come up with this dispersion relationship for the wave outside this dielectric region. Now you have the expression for the Z component of magnetic field. So all other field components can be known, but you need to match the boundary conditions. First, you apply the continuation of the tangential component of the Z H field at the boundaries, and then you can figure out all the coefficients. And then the next boundary condition is the tangential component of the electric field along X direction continuous. And for this, you can write down the characteristic relation between alpha and Ky. Once you have done this, then you come up with this characteristic relation. And this expression is very, very similar to the one we had for the TMO. So you can just plot the right-hand side and left-hand side on the sum figure as function of Ky. and then you look for the intercepting point to determine the available ky for the guided mode. And so at the cutoff, this alpha is going to be equal to 0, because at the cutoff, the radiation is no longer guided inside the waveguide. So there's no attenuation, there's no decay of the field outside the waveguide. So you set alpha equal to 0 to get the cutoff frequency, omega c, or here we spell it as the omega co. So if you set alpha equal to 0, then the left-hand side of this expression is going to be equal to 0. So you'll be looking for solutions from this tangent kyd over 2 equal to 0 right here. So with this, you can write down the cutoff frequency for the mole number m for this RT mole given by this expression. And you can see that no matter how you push the point toward this origin, there's always one intercepting point. So for this RT mole, there's no cutoff frequency for the first mole. You always have one mole propagating inside this waveguide. And I want to remind you that when you deal with the metallic waveguide, for TE and TM mole, there's always a cutoff for the first mole. In other words, if you reduce the wavelength, if you increase the wavelength or reduce the frequency too much, then the radiation cannot be propagated inside a metallic waveguide. But for this dielectric waveguide, you always can propagate RT mole or RTM mole inside the dielectric waveguide. Now, let's pick up the solution where you have the cosine-like solution for the H component, for the Z component of the magnetic field. Then you follow the same derivation process. You can come up with this characteristic relation like this. Now, on the right-hand side, you have a cotangent, and on the left-hand side, again, you have alpha over ky. And you can replace this alpha with the by using the dispersion relationship, so that you can have ky. You can just write down this alpha as a function of ky and also some material constants. So if you plot the right-hand side and left-hand side, then again you can generate this figure, and you look for the intercepting point of the red curve and blue curve to determine the solution for ky. And to find the cutoff frequency, you set this alpha equal to 0. Then you'll be looking for the solution of this cotangent, this expression equal to 0. So you can figure out the cutoff frequency for the mole number 1, number 2, and number 3. And you can see that this is the same as the even TM mole. There's a cutoff for the first mole, because if you move this point to a value less than this point, then you won't find any intersecting point on this figure. So for even TE mole, there's a cutoff for the first mole. 所以呢，在这个小节里头我们就是加强一下印象研读了一下这个 TE mole 相关的分析。那它的分析呢，几乎跟 TM mole 一模一样。那 TE mole 跟 TM mole 不一样的地方在于，就是这个在这个 axial direction 上头的话 ，TE mole 有一个这个磁场所存在。但 TM mole 呢，它是电场是有一个电场的分量是沿着 Z 的方向上头。那这两个分析呢都非常的类似，也就是你如果走过刚刚介绍的这个分析，譬如先把它把这个场的这个通式写出来，放进 Helmholtz equation， 然后呢你就开始把它分成这个R mole 跟 even mole 两个解下去算。然后再把这个边界条件带进来之后，你就可以找到一个这个characteristic relation。那这个 characteristic relation 呢，允许你用图解的方法来找出这个里头在跑的 mole 的 ky 的值。 那当这个 attenuation constant alpha 在 y 的方向上头变成0的时候呢，这代表这个里头的电磁波开始往外跑。那物理上呢，代表说你的 instant angle 已经开始小于你的这个边界的 critical angle。那所以呢，这个我们就是沿着这个相同的步骤呢，把这些东西分析出来。那就像这个 R 的 Tm mol 一样呢，这个 R 的 T mol 呢，并没有一个 cutoff frequency， 那这是跟金属波导不一样的地方。那这是这个小节里头的几个重点。